Well, it's time for a new James Webb Space Telescope update. And in this case, I actually wanted to focus on some of the major discoveries coming from the Milky Way galaxy, but specifically in regards to various nebula and the idea of star evolution, from the birth of stars all the way to their end. And that's because in the last few months, James Webb Space Telescope was able to capture some absolutely breathtaking images of quite a lot of well-known, gorgeous nebula. And though obviously we've discussed quite a lot of previous discoveries and talked about some of these images before, in this video I wanted to focus on some of the major discoveries in regards to the science behind these images and what exactly these images have taught us so far on how stars evolve in the Milky Way galaxy. So, hello wonderful person, this is Anton, and let's discuss various JWST nebula captured in the last few months. And let's start with one of the closest images to us, but also maybe one of the most breathtaking when it comes to the actual scale. This was released very recently, and it's essentially a close-up of a very well-known molecular cloud, Rho Oph, a gorgeous molecular complex containing approximately 50 young stars, with all of them surprisingly very similar in mass to the Sun, which in some sense basically shows us what probably happened approximately 4.6 billion years ago when the Sun was formed as well. It very likely started with a very similar molecular cloud. And at 390 light years away from us, this is the closest such object. But what exactly are we looking at? Well, I think the biggest structure here are these bipolar jets of molecular hydrogen, visible in red, that in essence are being expelled by various young stars in the middle. Now we'll actually discuss this in a few seconds, but in essence, once stars start forming in a lot of these complexes, they will often produce these very unusual, long tendril-like formations because of what happens right around the center of the star. We obviously think our Sun must have gone through this as well. Although some of these stars that you can kind of see in front have already sort of developed themselves, with many of them expelling most of the dust and very likely already developed into fully functional planetary systems. And so to some extent, this image shows us the beginning of everything for most stars. So pretty much every star around us began in one of these clouds. But if you were to zoom in on one of these stars, or essentially try to zoom in on one of these very long tendrils, you would most likely be looking at something like this. Now this is the second image I wanted to show you of an object known as HH211. HH stands for Herbig-Haro. And in essence, all Herbig-Haro objects have a very similar structure. This is probably the most famous one, the one we've discussed in one of the videos in the description. All of them are very young stars, possibly only a few thousand years old and still growing and developing. But just like your typical black hole or neutron star, because these are fast-spinning magnetic objects that also possess an accretion disk, they eventually develop these polar jets that travel through interstellar space at very high velocities. Now, if this was a black hole, the velocities would be very close to the speed of light. But because this is a baby star, here the velocities are much more modest. In this case, it's maybe about 80 to 100 kilometers per second. And based on the observations from similar Herbig-Haro objects, it became possible to analyze exactly what happens much closer to the center where this huge outflow occurs. And that's despite the distances. In this case, it's about 1000 light years away from us. And so here we seem to have an object that's about 8% the mass of the Sun, but it seems to be growing very rapidly. And that's actually because the accretion disk and the polar jets form a sort of a fountain around the star where quite a lot of material gets deposited into the star, but also quite a lot of it gets expelled in these jets. In some way you could maybe imagine it like this, a huge funnel powered by the magnetic field and the gravity from the star. But for this object, the outflow very close to the star is a little bit slower, which suggests that the materials coming out of there seem to be a little bit heavier. In this case, it's probably molecules and not just atoms. And so here, it's not just hydrogen, which probably moves much faster, but also much smaller, potentially organic molecules, including things like carbon monoxide. So in essence, there's a kind of a multi-level flow coming from the center of the star. There's obviously a flow of hydrogen, but there's also a flow that moves slower that seems to include much heavier molecules, which by itself shows us the next step in star evolution. Following the formation inside the molecular cloud, a lot of stars experience this for thousands and thousands of years, eventually evolving and developing into final objects, main sequence stars. Although in this particular case, scientists have also detected some kind of a wiggle, which implies that this is probably a binary system. Another object seems to be pulling on something in the center, creating an outflow that's not entirely straight. So we're basically observing a formation of a binary system. Although intriguingly, when it comes to star formation, a lot of these observations from various nearby molecular clouds show us something a little bit different from what happens closer to the center of the galaxy. And in the center of the Milky Way, there is a region known as CMZ, Central Molecular Zone, a region containing giant molecular clouds that seems to be 2000 light-years across and contains 60 million solar masses of material. And right there in the middle, there's an unusual region known as the brick. Something that looks like this if zoomed in. And so the recent observations by the James Webb were able to analyze this massive cloud gas that's sometimes referred to as the infrared dark cloud, showing us what's happening here as well. And generally speaking, these types of molecular clouds or these types of regions are extremely different from what we have much closer to the solar system. They're way more denser, containing a lot more stars, and potentially also a lot more star formation. Although the brick seems to be a little bit different. It shows less star formation compared to regions nearby, but seems to be just as dense and seems to contain just as much turbulence. But because this is such a dark region and because a lot of dust blocks a lot of light, it's always been a very difficult region to study. Nevertheless, despite being somewhat dark and appearing somewhat inactive, it seems to contain at least 56,000 stars that are being formed there right now. And surprisingly, this is actually on the lower end for this unusual central region. Many other locations here have way more stars being formed much faster. But previously all of this was kind of invisible. Now it is visible because of carbon monoxide, the gas that's very bright in certain infrared frequencies. And turns out that this brick region contains huge amounts of carbon monoxide that seems to act as a kind of a coolant. And since star formation usually happens in much cooler regions, especially in dense regions of similar gases, technically we expect a lot of stars to form here, because finding so much carbon monoxide generally indicates higher rate of star formation. But that's not what's observed here, because for some reason the gas here is a little bit warmer. And at the moment that's a mystery nobody can explain. So basically all of the gas present here should be forming stars, but it's not doing that, because something in the central region is warming everything up. Nevertheless, the discovery of so much carbon monoxide is definitely kind of exciting. The ratio of carbon monoxide to hydrogen is much higher than anywhere else in the galaxy. And so trying to understand exactly what happens in these regions and how the star formation here might be a little bit different is going to be one of the future goals for the James Webb staring at the center of the galaxy. Right now this is really more of a mystery that nobody still understands. And then we of course had some really exciting observations from the famous Orion Nebula. Specifically the Orion molecular cloud, where even more stars are forming, with many once again very similar to our Sun. And here the scientists discovered something that was really surprising. It's known as methenium, sometimes referred to as methyl cation. Basically a carbon compound that seems to be extremely important for organic chemistry happening in the interstellar space. And though it's not something that naturally exists on planet Earth, it seems to be absolutely crucial for theoretical explanation involving various complex organic molecules detected in outer space, including various amino acids or building blocks of life that were discovered by various telescopes in the last few years. The only way to explain their existence or how they could form is through various complex processes that must happen in outer space in various molecular clouds, which by the way is directly connected to the potential existence of life on other planets or even to evolution of life on planet Earth. Huge amounts of these compounds most likely came from outer space. And so by conducting observations in the Orion Nebula, a team of scientists discovered methenium hiding in plain sight, located in quite a lot of regions of the Orion Nebula, suggesting that it's basically performing a lot of chemical reactions right now, with the main focus being this unusual star named D203-506, some sort of a small red dwarf that's obviously still growing, and that's also receiving a huge amount of UV radiation from many nearby stars. These types of environments are very common in many molecular clouds, but these very massive stars producing UV light only exist for a few million years. They go supernova afterwards. And though these very powerful types of radiation are supposed to destroy a lot of different complex molecules, it does not seem to be the case here. Because it turns out UV radiation promotes the formation of methenium. And so once those stars disappear, in theory there's a huge amount of methenium floating around various stars and in the interstellar space, which is precisely what's been detected here as well. And what's really strange about this unusual molecule is that it doesn't react with hydrogen, but it loves reacting with a lot of organic compounds. And so it acts as a kind of a stepping stone for the formation of more complex molecules that then produce things like amino acids. Although in this case also showing us that UV radiation in general seems to be critical for the formation of complex chemistry in various molecular clouds. In essence, explaining how a lot of complex stuff must have formed in the solar system as well. So yeah, some really cool discoveries. But so far we've just talked about formation of stars. Now obviously James Webb has looked at various developing stars, but it also looked at stars very close to the end of their life, or even stars that have already transitioned into something else. And so here let's take a look at some of them. For example, there was the image of what's known as a Wolf-Rayet star, in this case WR124, that represents a massive star that's most likely going to go supernova in the near future. And here, as these stars evolve, they form these huge shells around themselves, even visible from a distance of 15,000 light years. Now this particular star is about 30 times the mass of the Sun, but it already released approximately 10 solar masses into outer space. That's what you actually see around it. And here the main point is trying to figure out how these various stars contribute to overall dust in the entire galaxy. All of this dust will eventually get recycled, forming new stars, and so trying to see what kind of a dust is being released is obviously kind of intriguing. Although in this case one of the main discoveries is just the observation of various very clumpy regions that seem to form as they're expelled from the star. It's not entirely clear where all of this goes just yet. But eventually the star is going to go supernova, and it's going to produce something similar to this. This is the other observation from the youngest supernova in the Milky Way. It's known as Cassiopeia A. This most likely happened about 340 years ago, but it looks like nobody on Earth might have actually seen it. We've talked about this a little bit more in one of the videos in the description, but one of the reasons is probably because it's kind of far away. 11,000 light years away from planet Earth. And so once these massive stars explode, they once again produce another beautiful dust cloud, obviously different from the ones we saw previously. And here it seems to once again produce these various clusters, or various mini bubbles, with a lot of really complex shapes, and more importantly, unlike previous clouds that usually contain light elements, here we have a lot of heavy elements, oxygen, argon, neon, and of course a lot of metals like calcium and iron. But here there are also unusual structures that are still kind of mysterious. For example, these unusual green protrusions that scientists are referring to as the green monster. It's not clear what exactly produced this, but they seem to be all over the place. And so in essence, by observing these supernova remnants, we're looking at the end of star formation as the stars evolve and as they finally release all of the heavier elements that they managed to create over millions of years. But in this case, this was very likely a much more massive star. What about stars like our Sun? Most stars out there are much less massive, and so they actually produce something a little bit different. And here we're talking about what's known as planetary nebula. This is the famous Ring Nebula, recently observed by the James Webb. Here this is an expanding shell of gas coming from the star in the middle that occurs when the main sequence star, like our Sun, first becomes a red giant, then becomes a white dwarf. Now this object is about 2600 light years away from us, but it's one of the most well-known planetary nebula and one of the most studied objects. Here the star in the middle is a white dwarf, approximately 0.58 solar masses in mass. It's also surprisingly really bright and very hot, 135,000 Kelvin, 310 solar luminosities. But this is something we've known before. But the James Webb was able to discover something else. For example, approximately 20,000 unusual dense clumps that you see right there that actually seem to contain almost half of the total mass released from the star. And quite a lot of the material here represents very complex organic molecules, such as for example the very important polycyclic aromatic hydrocarbons, a very important precursor that's responsible for forming everything inside our bodies. But the more detailed examination discovered at least 10 different arcs, suggesting 10 powerful emissions when the star was in its red giant stage. There are also approximately 400 different spikes that seem to have formed as a result of some kind of a turbulence. And surprisingly, there are also quite a lot of carbon-based molecules whose origin is currently unknown. Although some of these formations and some of this turbulence is most likely because this is technically a triple system. The central star has at least 2 companions, and the farthest one seems to be a red dwarf as well. But in this case, we basically get to see the other side of star evolution. The end of life for most stars out there, the ones that cannot go supernova. And in this case, they also recycle their gas, but different gas in somewhat different ways. Unlike a supernova that produces a lot of heavy elements, here we get a lot of organic molecules and a lot of lighter elements that then become interstellar gas. So super exciting stuff, and just like after what? 1 year of operations. So you can only imagine what we're going to find out in the next 10 years or so. I'm super excited about these future results, and I'm sure we're going to learn so much more about star evolution in the next few years. But there were of course so many other images captured by this iconic telescope. We've discussed many in some of the previous videos, and we'll definitely talk about other ones in some of the future videos as well. But before we finish this video, I wanted to mention a couple that were not in the Milky Way, but also showed us something really important. One of the most important observations was actually a combination of James Webb and the SOFIA telescope that's now officially retired. This was the observation from the iconic Tarantula Nebula, and specifically the cloud known as R136. This is where we find huge amounts of massive stars, and basically the most massive stars discovered in the entire universe. Now here, this is what the new image looks like. It shows us the magnetic fields and the interplay between magnetism and the gravity. And because these are very complex magnetic fields, they seem to produce very surprising results. They basically seem to prevent certain gases from forming stars in certain regions. Now first of all, this nebula is forming stars ridiculously fast. It actually kind of mimics what happened in the universe approximately 11 billion years ago. But if you look at this image, you'll see that in some regions there are no stars, which was a bit of a mystery at first. Turns out that a lot of these regions seem to also have powerful magnetic fields. These regions resist turbulence and prevent gravitational collapse. And so only in the regions where the field is much weaker, the gas is able to escape and eventually form stars. But here, the power of the magnetic fields definitely acts as a kind of a switch for star formation in the entire cloud, while also potentially holding everything together. Technically, the cloud should have fallen apart a long time ago. And intriguingly enough, most of these fields are produced by the stars themselves, or specifically by various activity very close to them, so in some sense it's a kind of a feedback mechanism. More star formation leads to more stars, leads to more magnetic fields, which then can actually shut down star formation in certain locations. So definitely some intriguing results, but still not super clear on how all of this works. And since we've talked about the Large Magellanic Cloud, here's also a picture from the Small Magellanic Cloud, another beautiful star-forming region containing thousands of stars. In this case, one of the most exciting discoveries here is the presence of thousands of different filaments in this region known as NGC 346. And as I mentioned in the beginning of the video, all of these filaments are very likely baby stars with very powerful jets. Basically gas that's being blown away from young stars, as many of them seem to form around the cloud. Although in this case, what's exciting about this cloud is that it seems to have a lot of material that's somewhat primitive, very similar to how it was billions of years ago, making this one of the most interesting star-forming regions visible from planet Earth. Something we'll probably come back to and talk more about once there are more discoveries. But I guess, at least for now, or until future discoveries, these were the main discoveries from the last few months in terms of star formation, star evolution, and star demise when it comes to the Milky Way and nearby galaxies. A lot of really exciting stuff, a lot of really exciting mysteries, and lots of beautiful images. We'll definitely come back and talk more about this once there are even more. Check out some of the previous videos from the James Webb in the description below. Thank you for watching, subscribe, share this with someone who loves learning about space and sciences, come back tomorrow to learn something else, support the channel on Patreon by joining channel membership or by buying the wonderful person t-shirt with the James Webb as one of the designs in the description below. Stay wonderful, I'll see you tomorrow, and as always, bye bye.